Hello everyone. First of all, thanks Kaggle and the host for providing this opportunity. And it's very honorable to give the presentation about my solution. And let's see what we will talk about in the next. There will be 6 parts in total, as listed in this slide. I will give an introduction in the first, and then share the key idea, and then about the mode, example and training, and the last QA. I have some background about physics and optical engineering, and I have worked as a computer vision engineering for several years in a China company. After the BirdCLEF 2024, I become a competition grandmaster. Let's see the key idea. Basically, I use the method the same with the previous competition, the HMS, the harmful brain activity classification. By utilizing the raw signal and the spectrum data. And also I trained the mode with different seeds and different model structures to add diversity. Enter the mode. Let's see the mode, how I designed the models. Three type of models were developed, including raw signal mode, spectrum-based model, and a mixture of these 2 parts. There is not too much tricks about the spectrum-based model, so I will introduce more about the raw signal input model. We take a sequence data as an example, a one-dimensional array. It could be a sound wave or other type of signal or other type of input data. And here we take an array of 32 elements as an example, like this one. And then we can divide the array into 2 groups, and one for all the positions and the other one for the even position. And then the data becomes to an array with a shape 2 by 16, like the red and the blue. And then we can reshape each row of the data into a square matrix as this figure. Then it can be treated as a 2-channel image and then be fitted into the vision mode. Like the figure show at the shallow pink region, a 2-dimensional conv kernel applied on this figure, on this image is equal to a special one-dimensional conv kernel that applies on the raw signal. As what we have talked about just now, and in this competition, the wave is 160,000 long, and then the input size for the vision mode after the packing reshape operator, the actually input shape is 2 by 80 by 1000, and the parameters are set by after some experience, and it's best in this situation. And then I will talk the model, the inference pipeline. And the left figure shows the raw signal mode is after the packing reshape we just talked about, and then feed it into a vision mode. Here is a HGNet B0, and then geometry pool and then do the prediction. It scores public leaderboard 0.72 and in the private is 0.66. And for the spectrum mode, there is nothing special. The pipeline is quite simple. The input is raw view, and then doing mail transform with FLT equals to 4096, and the thread is 512. And then fitted it into the F-Synthetic B0. And then for the limitation of the time, I just use 105 to do the final inference. Otherwise, it will become the timeout. This spectrum-based model get 0.7 in the public leaderboard and 0.67 in the private leaderboard. And the last one is the mixer model. It's a two-branch structure. The left branch is the same with the spectrum-based model, but a reset step is added to reduce the inference time. If we keep it all the same with the previous spectrum model, it will become timeout. The red branch is the same with the raw signal model. And at the last concat the last feature of all these two branches and make the prediction. And it scores about 0.7 in the public leaderboard and 0.66. And then come to the example. There are 3 models and 5 weights in total for the final inference, and 3 for the 3 weights for the raw signal model, and 1 for spectrum, and 1 for the mixture. And the different backbone were used here, including HGNet B0 and FSNet B0. I didn't talk too much about the ensemble weight. Just set them by hand. And 0.5 for the raw signal mode, and 0.4 for the spectrum-based model, and for the mixture, and it is 0.1. Let's see, and then it's about the training method. And about the data, when training, 5 seconds data were randomly sampled, and when doing validation, the first 5 seconds data were used. And if the max value of the sound wave greater than 1, and then divided by the max value, and I use probability equal to 1 with mix-up, it helps a lot there. For the spectrum-based data, I use cutout for augmentation. And all of my model training basically follows the same pipeline. 50 epochs with BCE loss. The optimizer is AMW. Is AMW with decay. The initial learn rate is 0.001 with a cosine schedule, and warm up 800 iters in the first 800 iters. Both modes are trained with fail files, but for the time of inference limitation, a subset of the weights were used for the final inference. And another tag I use here is the checkpoints average, and it helps a little here. Wait a moment. Here it says that I tried, but not work very well. The first one is piece level. I think there it should work fine, but I didn't spend too much time on this tag. And if I got more time, I will spend some days with piece label. And
like a pseudo labeling.
yeah.
Yeah, interesting. Yeah.
And filter, I tried different filter. For example, 0.5 hertz to, but it didn't help. I don't know why. Maybe because of the data distribution. And I also tried randomly scale in amplitude. It didn't help too much. Basically, no effects on the final result. And here is my solution.